So chapter 30, sources of magnetic field. This is the last chapter in electromagnetism. We still have 2 other chapters related to optics and not to electromagnetism. So you all know that there are 2 sources of magnetic field, either magnets, okay, or electric current. You all know that B vector, which is the magnetic field or the symbol of the magnetic field, can be created either by a magnet, a pure magnet, a real magnet, or by a current. Okay, there's a scientist called Ørsted in reality. This scientist was doing an experiment. He was doing a circuit, I guess, with some generator and some resistors, etc. He was doing just a circuit, a normal circuit, and there was a compass beside his circuit. And he has noticed that whenever he closed the switch and the current flowed in his circuit, he noticed that the needle of the compass deviated. So because of that, he deduced that there must be a magnetic field generated by the circuit or by the current moving in the wires of the circuit. So here came the idea of Ørsted, and he started testing if really a current creates a magnetic field. And we arrived to this lesson, which is related to the discovery of Ørsted. بكل الأحوال, this discovery is very, very important because instead of using a magnet to create a magnetic field, scientists can use for experimental study wires or coils or etc. Anything. They can use currents to create magnetic field, and they control the magnetic field by controlling the currents passing through the wires. So this is very useful for scientists who aim to use magnetic field in their research, in their study, in everything. So what's our job in this lesson? Our main aim in this lesson is to study the magnetic field created by a current, not the magnetic field created by a magnet. We don't care for it. Only the magnetic field created by a current. We're going to find its direction, its magnitude, its sense using different methods. Similar to finding the electric field, for finding the electric field, we use 2 methods. Okay, so Coulomb's method and Gauss law, we use these 2 methods to find the electric field. So integral k dq over r squared ui. So this is the first method of coming from Coulomb. And the second one was using Gauss law, integral e dA equals a q enclosed over epsilon 0. So this is for Gauss's law. Now to find B vector, there are also 2 methods. One called the Biot-Savart law, I will explain them, and the other one is called Ampere's law. Ampere's law is similar to Gauss's law, somehow similar, يعني a similar idea. And Biot-Savart law is something similar to similar to Coulomb's method, which is by integrating, taking a small portion and finding the effect of the small portion on a point of study and then integrating the whole quantity B or E. It depends on what we are calculating. Okay, so this is for B vector. So we are going to learn 2 methods to calculate B vector, Biot-Savart law and the other method, Ampere's law. So let's start. Let's start first with magnetic field created by a moving charge. Okay, so if we have a charge Q, this charge is in motion, they notice that a magnetic field is created around this charge Q. So let's take this point M. You can see this point M in the figure. We have charge Q. This charge Q is moving with a speed or velocity V. So at point M, there is a magnetic field, which is given by mu0 over 4 pi QV. I will explain all the terms. QV cross UR over R squared. So this is B vector, which is at point M. Point M is situated at a distance R from charge Q. For sure, when Q moves, the value of B at m will vary as function of time. This is true. Okay, so because the magnetic field depends on R, assume V is constant. It depends on UR, so this is B. Let's explain the terms. B vector equals to mu zero. Mu zero is called the permeability of vacuum, which is a constant. This is a constant for vacuum. By the way, each medium has its own permeability. We only study magnetic fields in vacuum. We never study magnetic fields in other media, only in vacuum. So similar to permittivity of vacuum, which is epsilon zero, which is related to electric field, we have mu zero, which is called the permeability of vacuum, which is related to magnetic field. اوكي سو هيدي بتشبه الابسلون زيرو. الابسلون زيرو اللي هي انا بستعملها لما اكون عم بحكي عن الكتريك فيلد، بتبين معي بالشغل. هاي الميو زيرو بتبين معي بالمagnetic field. Mu zero is simply a constant related to the medium, which gives how does this medium interact with the magnetic field. Okay, or how does this medium help in affecting the lines of field. So this is mu zero. It's just a constant and it never changes. Q is the charge for sure. V is the speed of the charge. R, it's the distance between the charge and the point of study. UR is a unit vector directed from Q to M. This is UR. So you can see I don't know if you know the cross product. I don't know if you know this cross product. Did you study cross product?
No.
No? Okay. So cross product is different from dot product. Dot product, for example, it's like a C vector equals A dot. So let me write. So this is a scalar product or dot product. So scalar product, or we call it a dot product, is something like this. C vector equals A dot B. This is called scalar product. So C as a magnet, sorry, this is not a vector, it's a scalar. Sorry for this. This is a scalar, so this is not a vector, it's just a number. It's equal to A, B times cosine theta, which is theta, the angle between A and B. You all know this information for dot product or scalar product, called also dot product. هلا cross product or called vector product, this is cross product, or it's also called vector product. It's not a scalar، منه رقم مثل فوق، هو vector بالحقيقة. So بنقول C vector equals A vector cross B vector. أو بتنكتب ك like multiplication symbol like this. So C vector equals A vector cross B vector. So what is this C vector? Simply, the cross product is defined by that C vector is perpendicular to the plane containing A and B. Okay, so C vector is perpendicular to A and B. It's perpendicular to the plane containing A and B. And the magnitude of C, this is the division of the cross product, okay, or vector product. The magnitude of C is equal to A, magnitude of A, times magnitude of B, times sine the angle between A and B. Not like the scalar product, it's a cosine, no, it's a sine. So this is in general for cross product. Don't worry, when we work in them, we will only need the magnitude. So we will need the magnitude of the cross product. So you will be familiar with that with time, don't worry, okay? So this is the magnetic field created by a moving charge. If V is equal to 0, and if the charge is not moving, you can see that B will be equal to 0. So if V is equal to 0, then B is equal to 0. What do we deduce? We deduce that if the charge is not moving, it will not create a magnetic field. It will only create a magnetic field if it is in motion. No motion, no magnetic field. If it is in motion or at rest, it will create an electric field. تعرف إنه في E عندي أنا. الإي أنا بلاقيها نحن كلنا نعرفها KQ over R square. This is the electric field E. أما إذا كانت in motion, if it is moving, then there is a magnetic field created by this charge Q around it in space, and this B depends on the speed of my particle. So this is the first note. No motion, no magnetic field generated. Second note, you can see that if the angle between, I've said that B vector, so here's the magnitude, so you can see, just I'll explain the second note again, بس لا أشرح الفكرة قبل. So we said that, let's how to draw B vector. So we have said, depending on the cross product, we have to draw B vector perpendicular to the plane containing V and UR. So you can see here, let me erase just the things that I have written. So you can see here that because V and UR lie in my plane, they are both in my plane. So we have drawn B vector coming out of the page. It's coming out of the page لعنا. يعني السهم لعنا. You all know this information that if we have a vector and if it is coming out of the page, we draw it as a dot in a circle, and if it's entering the page, if it's drawn like an X in a circle. So إذا كان جاي لعنا بنرسمها نقطة، وإذا فايتة لجوات الصفحة بنرسمها X. Okay, دايما. هلا because B vector is perpendicular to V vector and UR vector, and both V vector and UR vector lie in my plane, so B vector can only be drawn inward or outward, not بنرسم غير هيك. So this is most of our cases. Most of our cases are like this. So you will be familiar, don't worry. So B vector is drawn. طب how do we draw if B vector is outward or inward? I'm calculating, or I'm finding B vector at point M. Simply, cross product says, I'm not able to explain them very well because you can't see my fingers. I have to use my fingers, but I already know that you know the electromagnetic force. For sure, you remember Laplace force. Laplace force, which is IL cross B. You used to use your three fingers. The first one with I, the second one with B, the third one with F, so you get Laplace force. Here is a similar thing. Use the same method for the three fingers, making them as right angles. The first finger, so this is our hand. Use your right hand. Okay, I will explain this when I upload the recorded session. They all show my hand, how do I do things. Okay, so I will explain them in details. So when you use your right hand, the first finger goes with QV. So this is QV, يعني it goes with V, but if Q is negative, so it goes opposite to V. This يعني with motion. The second one, it goes with UR. So the third one will go with B. This is the definition of a cross product. So you all know this. For example, if we have, you all know Laplace, F equals IL cross B. You all know this. So this is a right hand rule. The first one goes with I, the current I, or IL if you want. The second one goes with B, and the third one goes with F. You all know this. It's similar. Okay, so this is the first finger, one. This is the second finger, and this is the third finger. This comes from the definition of a cross product. هو الكروس product هيك نحن ما خصنا. So even if we have C vector equals A vector cross B vector, my first finger goes with A, the second finger goes with B, and the third finger, or the middle finger, goes with C. So this is the definition of a cross product. So how to find B vector? Now I want you to try it. I know I don't see you and you're not able to see me, but I will re-explain this when I show you my hands when I upload the recorded session. So first finger, the thumb goes with V. Try it, okay? The second finger goes with UR. You will see that B vector will be directed out of the page. رح تيجي ال B vector لعندي أنا. Okay? So did you try it? Is it okay?
Yes.
Okay, great. So this is how to find the direction of B vector. So we have said that B vector is perpendicular to a plane containing V and UR. B vector is determined by right-hand rule, three fingers together. The magnitude of B is given by, from the definition of the cross product. So we have seen that B equals mu 0 over 4 pi QV cross UR over R squared. So the magnitude is simply mu 0, this is the magnitude, over 4 pi. So QV, so magnitude of V is simply V. Magnitude of UR is simply 1, okay? So the magnitude, this is the magnitude of V. The magnitude of UR, this is 1, because it's a unit vector. Sine theta, where theta is the angle between UR, so theta is the angle between V and UR. So this is for theta. So you can see here, theta is the angle between V and UR. So this is the magnitude of B at point M. We have to indicate كمان something important, that if sine theta is equal to 0, no magnetic field will be generated. What does this mean? يعني إذا ثيتا كانت 0 أو ثيتا كانت باي, okay, so no magnetic field will be generated. So for all points that are found in front of Q, so إذا أنا عندي point هون, هيدي الpoint, let me call it M. If my point M is in front of Q, so you can see in this case I will draw UR, دايما UR from, this is UR in my case. So the angle between V and UR in this case, so this is case 1, let me call it case 1. Case 1, where M is found in front of Q, you can see that the angle between UR and V in this case, it's equal to 0. So theta is equal to 0. So if theta is equal to 0, then sine theta will also be equal to 0, which means that the points that are along the same direction of motion of Q will not examine any magnetic field. No magnetic field is created there. Only on the points that are above or below. طب كمان if the angle is behind Q, so if the point is behind Q, let me call this is case 2. So if the point is behind the Q, so let me draw UR in this case, this is UR. Where's my angle between V and UR? You can see my angle between V and UR. So theta in this case, it's equal to 180 or pi degrees, so pi radians. Sine theta, it's equal to 0. This means that B is equal to 0. So the points that are along the same direction of motion of Q, in front of Q or behind Q, all of them will examine no magnetic field. The magnetic field will only be created on, يعني not on the direction of motion of Q. مثل ما شايفين على point aside from the line of motion of Q. So this is for a point in motion. So we have to keep in our minds two things, that the magnetic field has this magnitude, okay? It's created not along the direction of motion of the point, and if the point is not in motion at all, no magnetic field will be created. So if I've written here, so if V is equal to 0, B is equal to 0, this means that the particle is not in motion, so it will not create a magnetic field. If V is parallel to UR, which means that the point I'm studying is behind or in front of my point of my moving charge. So بهذه الحالة كمان, if the point of study is along the direction of motion of my point charge, no magnetic field كمان will be created at this point. So بهاي الحالتين ما بيكون في عندي magnetic field. Okay. So let's now learn the magnetic field created by a current, which is law of Biot-Savart. It's the same law, but we are going the same يعني equation as before, but we are going to generalize it from the motion of a charge or single charge to motion of a current. You all know that a current is a group of charges, so we can do that. Let's do it. Similarly, an electric current can produce a magnetic field. So if a moving charge can produce a magnetic field, then a current which is group of moving charges, will also create a magnetic field. So as I have explained earlier, this was first demonstrated experimentally by a scientist called Ørsted. Okay, so how to deal with this? We're going to divide our wire, which is carrying current I, into small portions, as you can see. Each portion is carrying a charge dq. So this is my small portion, it's carrying a charge dq. We have learned that this dq will create at point M, this is point M here, so this is point M, a magnetic field dB. Why do we call it dB? Because Q is the total wire. dQ is only a small portion of my wire. So dQ will create, because it is in motion, dQ is moving with a speed v. This is a current in motion. dQ is moving with a speed v. Will create a magnetic field at point M. And this magnetic field at point M will be given by mu0/4 pi, I'm reading down, QV cross UR over R squared. This is the same formula as before, but instead of Q, I've written DQ, and instead of B vector, I've written DB vector. Why? Because I've divided my entire wire into infinitesimal portions. Each one of them is carrying a charge dQ, and the generated magnetic field is called dB. The aim is to find the total magnetic field at point M لكل الواير مع بعض. So I have to integrate. Instead of keeping dq, because we don't like to keep dq because dq is not given. Usually what is given is the current. So we try to relate dq with the current. You all know that dq it's equal to I dt from the definition of the current. I've explained this command last time when I explained the current. So I equals dq على dt. I equals dq على dt. So dq will be I dt. We can write dt, or we can write dl vector equals v dt. What is dl vector? dl vector is a small portion, infinitesimal portion, tangent to the direction or tangent to the wire. يعني a small current element. يعني راح يمشي مسافة dl. dq لما تكون سرعته dv أو سرعته v, it will move a distance dl. dl is drawn tangent to the wire. Okay, this is a current element, dl. What is v? v is the speed of my charge. So instead of dt, I'm writing dl vector over v vector. I will repeat again. What is dl vector? dl vector إذا بدكم تعتبروها هي المسافة اللي راح يقطعها dq خلال وقت dt. كفكتور بتنرسم vector tangent to the current. v is the speed of the charge. So cross multiply, you will get, I've said dq equals I dl. dl, again, it's an infinitesimal vector tangent to the trajectory at a certain point. So over v, so cross multiply, you will get dq times v equals I dl, like this. So I will substitute this instead of dqv. I will substitute. So we will get dB equals mu0/4 pi I dl cross UR over R squared. So هيدي بس حطيت مطرحها أنا Q dV. So it was a dQ times V, like this. So this is dB. Now, if I have to find the magnitude, then the magnitude will simply be mu0/4 pi I dl over R squared. dl, it depends on the shape of the wire. If it's straight, dl, similar to electric field, dl will be, if it's along x-axis, it will be dx. If it's along dy, it will be dy. dl, I'm talking about dl. R, what is R? It's the distance to the point. It's similar to the magnetic field, to the electric field, and it's even easier. You will see it's even easier. Okay, so sine theta, it's the angle between dl and ur. Okay, so this is for the given. So this is sine theta angle between DL and UR, because the cross product we have DL cross UR. So if we have to find the total magnetic field M, we have to integrate by the whole wire, we have to integrate everything. And this is for B vector. Okay, so this is the first method, which is the method of Biot-Savart law. When to use this method? If you see, for example, infinite wire, it's okay to use it. Segment, always use it. If it's an infinite wire, you can use both Ampere or Biot-Savart. Okay, if it is a segment, only use Biot-Savart. If it's an arc, a circle, use Biot-Savart. Okay, Biot-Savart. What do we have? Segment, semi-infinite, you can use Biot-Savart. So these are the cases where do we use Biot-Savart law to find the magnetic field at a certain point. Now let's see the magnetic force. Repeat them again. I will repeat them when I solve, but I will repeat them again. The only thing that in this course we will solve using Ampere's law is the infinite wire. يعني هو الانفينيت واير رح نستعمله بس لأمبير. All the other things use with them Biot-Savart law اللي هن segment, semi-infinite, circle, arc of a circle. هيدول Biot-Savart law. Okay. Let's talk about the magnetic force between two parallel conductors. So this part here, it has been a long time we did not ask about forces, but I explain them anyway because it has no meaning to explain the magnetic field without talking about the forces. Anyway, you all know Laplace force, so this is the same. Magnetic force between two conductors. So assume now we have two conductors, 1 and 2. These two conductors, each one has a length L, and they are separated by a distance D, and they are carrying currents I1 and I2 moving in the same direction. So you can see I1 and I2 are both moving upward. So I1 will produce a magnetic field around it in space. This is what we have explained. Current produces around it in space a magnetic field. The magnetic field created by an infinite wire or a large wire is simply mu0 I over 2 pi d, where d is the distance and if I have a wire, this is my wire, it's carrying current I, this is a point M. So at point M, B at point M, it's equal to mu0 I over 2 pi d. This formula will be derived in our work in exercises. Okay, but you have to memorize it because you use it too much. Okay, so memorize it, keep it in your mind. We use it too much. Each time you have an infinite wire, B is equal to mu0 I over 2 pi d. So this is B. هلا ال1 will create a magnetic field at 2. سميته أنا B1. B1 can be found by right-hand rule. It can be found by something called curl right-hand rule. كمان I will explain this when I upload the video so that you can see my hand. How do I find the right-hand rule? So simply to find the direction of B1, you have to curl your hand with I1. So you place your thumb with I1, try to rotate your hand. You will see that B1 will be going inside the page. Okay, so B1 will be going towards the page, and its value is mu0 I1 over 2 pi d, where d is the distance again between the two wires. So ال1 رح يخلق magnetic field على ال2 وكمان ال2 رح يخلق magnetic field على ال1. بما انه صار عندي انا current وحامل magnetic field, it will be subjected to a force called electromagnetic force or Laplace force. يعني I2 حامل current I2 أو wire 2, it's carrying current I2 and subjected to magnetic field B1 coming from 1. So there's B external coming from an external source and a current carried by the wire. So it will be subjected to a force F exerted by 1 on 2. How to find F exerted by 1 on 2? This is simply Laplace force. So F exerted by 1 on 2, it's 1 on 2, it's simply I2 IL cross B1, like this. This is how to find the direction of F. Place your first finger with I2. So this is the first finger with I2. The second finger goes with B2 towards I2 لفوق إصبعكم your thumb upward. Then your pointer towards the page and your second finger inward. Okay? Your third finger will be, or the middle finger will be to the left. You can see this is how we draw F1 on 2. Similarly, we draw F2 on 1. So كمان F2 on 1, how to find it? F2 on 1. It is I1 L cross B2. So simply I1 is upward, okay? B2 is out of the page. So place your pointer out of the page. And I1, your thumb upward. Your pointer out of the page, you will get F2 on 1 towards the right. So this is how we find the force using the right-hand rule of the 3 fingers. Each time you see a cross product, you use the 3 fingers. Okay, so each time you have I and you want to find B, you can use the curl right-hand rule. I will كمان explain this when I explain the answers, how to find them. Okay, so don't worry. Now conductor 2 carries a current I2 and is placed in the magnetic field B1. So conductor 2, I've explained this, is submitted to an electromagnetic force determined by Laplace. F1 on 2 is equal to I2L cross B1. Okay, so this is F1 on 2. Similarly, the direction of F1 on 2 is perpendicular to the plane formed by 2 and B1. So I won't repeat this information, you all know them. Stands determined by right-hand rule, and its magnitude, it's equal to I to L B1 sine 90, where 90 is the angle between L and B. الزاوية ما بين ال L وال B. ال L يعني الرod وال B, it is the magnetic field. So B1 is simply mu0 I1 over 2 pi d. It's the magnetic field coming from wire 1. Multiply, you will get mu0 I1 I2 over 2 pi dl. You can do the same for F2. You will get F2 on 1 as a magnitude equal to F1 on 2. This must be true because F1 on 2 and F2 on 1 are action-reaction pair according to Newton's third law. Okay, they must be equal in magnitude and opposite in direction. Otherwise, we have something wrong. So if we do the same for conductor 1, راح نقول conductor 1 is placed in magnetic field B2, and this B2 is coming from wire 2, so it is subjected to a force F2 on 1 equals I1 L cross B2. If you do the same, you will get the same magnitude of the force. So this is a conclusion that the two forces, they have the same magnitude, they are an action-reaction pair. So this is, I'm not taking too much time to explain this because it has been a while we did not explain, we did not ask about forces. So just take a look on it and that will be enough. Okay. You can notice that if try it at home or when you're alone, if we have I1 and I2 going both of them upward or both of them forces, both of them inward, يعني راح يصير في كأنه في attraction between the wires. If one of them is going upward and the second is going downward, the forces, use your right hand rule, okay, you will see that the forces will be opposite in direction outward. Okay, so as if both currents or both rods are repelling each other. So if they are moving in the same sense, we have attraction. Our conductors are attracting each other. If they are moving in opposite senses, we can say that conductors are repelling each other. So this is just an observation or a notice. Okay. Now, Ampere's law. This is the last slide. For Ampere's law, as I have said, there's a second method to calculate B vector. This is mainly used for things that are symmetrical. We used to calculate cylinders إلى آخره, currents moving in cylinders, but cylinders is no more required since the pandemic. So we just stick to studying a wire only, not a cylinder. So you can use Ampere's law whenever you have an infinite cylinder, an infinite wire, etc. These are the only cases where we use Ampere's law. It must be symmetrical for sure in order to be able to solve the integral. Otherwise, if our problem is not symmetrical, the integral cannot be solved. Okay? When an arbitrary path encloses current, so here there's a difference between Ampere's law and Gauss's law. In Gauss's law, we used to choose a closed surface. Here we are going to choose a closed curve, a closed line, okay, closed path. So see that هيدا السي اللي شايفينه انتو, this is one dimension, يعني هيدا اعتبروه wire, خيط. This is an imaginary, يعني imaginary path. It's one dimensional. إذا بدكم مش surface, يعني هيدا طول length L. بهيدا اللينث يعني احنا بناخده بالعاده احنا سيركل. So أنا بالعادة باخده سيركل. أنا أخده عشوائي, بس إنه we can take it arbitrary in form. It's not wrong, but it will be hard to be solved. So to be able to solve it, we choose it usually circular, concentric with the wire. So this is simply a wire, and we apply Ampere's law. Ampere's law says integral BDL equals mu 0 I enclosed. I will explain each term. What is B? The magnetic field created around the wire, which is crossing this curve, or curve that I have drawn. DL, an infinitesimal vector tangent to my curve. I enclosed is the current enclosed inside my loop that I have chosen. Okay, so simply what's enclosed here? This is I. This is the only I that's passing here. So if I have, for example, another wire, this is, for example, I2. So I enclosed will be simply I1 plus I2. It's easy. What is DL? نحن كنا هونيك نقول EDS. DS كانت تكون perpendicular للsurface. Now DL is tangent to the curve. Tangent to the curve and not perpendicular as DS. Okay, كمان B in all the problems here will be tangent كمان to the curve and not as E vector perpendicular to the surface. Okay, so in these cases you will see that B and DL, both of them in all our problems will be both of them tangent to the curve that I choose. So don't worry, and the angle between them will be 0, and B will go outside the integral, and we simply have to do DL. If I have a circle, integral DL will be 2 pi r, length of a parameterless circle. That's it. Okay, so Ampere's law holds for any closed path surrounding any configuration of electric conductors. كمان one small note, if we have more than one wire, let me erase. If you have, for example, another wire which is moving, let me say I prime, moving in opposite direction to I enclosed in this case will be I minus I prime. Kمان I will explain this when I solve. So because they are moving in opposite directions, if the currents are moving in opposite directions, I enclosed is the algebraic sum and not the sum, a normal sum. It's the algebraic sum with signs. Okay, and the magnetic field will be similar or will rotate depending on the one with higher current. So this will be explained when I solve. Okay, so this is for our chapter.